So last time we had solved the Schrodinger equation. We had solved the Schrodinger equation for the binding energies of the electron to the nucleus. That means if I write the generic Schrodinger equation down here, what we found was what this E was. And we found that it had a nice analytical form, that the energies, the allowed binding energies, were quantized. They were quantized by that principal quantum number n. And so we can write those allowed energies as E sub n is minus R sub h over n squared. All right, so n is this principal quantum number. And n runs from 1, 2, all the way up to infinity. All right, today what we're going to do is we're going to look at the solutions to the Schrodinger equation for this, for the wave function, for the wave. And remember, we said that the wave, in some way, represents our electron. And today we are going to talk about exactly what is the meaning of the wave function. But before we do that, I have to tell you that when you go to solve the Schrodinger equation for the wave function here, what happens is that two more quantum numbers pop out. All right? And one of the quantum numbers that pop out in the solution to the wave function, for the wave function, is a quantum number we call L. L is the angular momentum quantum number. It's called the angular momentum quantum number because it in fact determines how much angular momentum the electron has. It is a quantum number, which means it has allowed values, very specific values. The allowed values of L are the following. They are 0. Unlike n, the lowest value that L can have is 0. 0, 1, 2, 3, all the way up. But it's got a limit. L's got a limit. The limit is n minus 1. So L can never be larger than n minus 1. It's tied to the principal quantum number. Why is it tied to the principal quantum number? Well, notice that only the principal quantum number tells you about the binding energy. It tells you about the total energy of this electron interacting with the nucleus. Whereas the L, the quantum number L, the angular momentum quantum number, it determines how much angular momentum the electron has. And in a classical picture, you may be familiar with the fact that if something's got angular momentum, it has rotational kinetic energy. And since the total energy is that rotational kinetic energy plus potential energy, well, then L is never going to be as large as n, because otherwise then the electron would only have rotational kinetic energy and no potential energy, and that wouldn't work, right? So that's why there's a limit here to L. It is as large as n minus 1, because you have to leave some energy to be potential energy here, right? Okay. And then finally, we have the third quantum number. And that third quantum number we call M. And it's the magnetic quantum number. And it's called magnetic because, in fact, it does determine the behavior of an atom in a magnetic field, although we're actually not going to take a look at that. But more specifically, what M is the z component of the angular momentum. All right? It's the z component of the angular momentum. And its allowed values are the following. its allowed values are m equals 0. All right, so just like L, it can have a value of 0. Plus 1, plus 2, all the way up to plus L. All right? So, hey, look at this. The magnetic quantum number is tied to the angular momentum quantum number. Why? Well, because this is the z component of the angular momentum, or it dictates the z component of the angular momentum. L dictated the total angular momentum. Well, the z component of the angular momentum is never going to be bigger than the total angular momentum, so that's why m is tied to L. And of course, when we talk about a component, hey, we're going to have a direction here too. And so these quantum number m can be 0, plus or minus L, plus or minus 1, plus or minus 2, all the way down to plus or minus L. All right? So that is it. We've got to have 3 quantum numbers here to really explain our system. All right? The reason we have 3 quantum numbers is because we have a 3-dimensional system. So it a little bit makes sense that you've got to have 3 quantum numbers to really describe the hydrogen atom here.